Hello dear learners, I am Dr. Nishant Yadav. Welcome to this course of Essentials of Surveying Applications and Technique. In this class today, we will start a new topic, that is trigonometrical leveling. This topic is essentially an integration of concepts of leveling which we are in the process of learning and the trigonometry which probably you would have studied in higher secondary schools. Leveling, as we know, is the fundamental technique in surveying which involves determining the levels of points which can be above or below the earth's surface, or it can be the difference in elevation between two or more points. This process plays a crucial role in various fields such as construction and engineering. By precise measuring height variances, leveling helps to create accurate topographical maps and contribute to build stable structures. Not just this, Army also uses the level to prepare hideouts and bunkers in strategic locations. The objectives of learning is to establish a reliable reference plan known as the datum, from which height differences are measured. This is essential for construction of roads, structures, and other infrastructure projects that requires precise elevation data. Leveling also aids in flood plan mapping, ensuring that construction is carried out safely and in compliance with regulations. Fundamentals of leveling involves use of an optical instrument such as a level or a theodolite, which can provide a horizontal line of sight and a vertical scale, as you can see in the picture. With few measurements and calculation, the vertical difference between 2 points can be obtained. There are various types of surveying, which includes direct leveling, trigonometric leveling, barometric leveling, and stadia leveling. For now, we will focus on trigonometric leveling. In differential leveling, also known as direct leveling, the process which involves physical measurement of height difference between points using a leveling instrument. This method is highly accurate and is commonly used for precise measurement over short distances such as small construction sites. The process starts with calculating the level of line of sight, for which the leveling staff is placed at a point whose elevation is known. Such point is called as the benchmark. Staff reading is recorded at benchmark and it is called as backside reading. To calculate height of instrument, that is the reduced level of the line of sight, the backside reading is added to the RL of the benchmark. Then the staff reading is recorded at the other point, where the level is to be determined. This reading is called as foresight. To calculate the level of the other point, we calculate it by foresight reading is subtracted from the height of instrument. When we find level of any point with reference to point of known elevation, it is called as reduced level. This is a simple operation of leveling, but the life of civil engineers or surveyor is not that easy. During survey work, we encounter various complexities and site situations which are not favorable. Sometimes points are not accessible, sometimes distances are not measurable, ground surfaces may be undulated, or it may be sloping. In such cases, measuring horizontal distance is tedious and sometimes it is impossible. The civil engineers are very smart. They will find ways to solve issues and how they can complete the work by means of direct or indirect measurements. By using the principles of triangles and trigonometry, surveyors can determine the height of locations that are otherwise hard to access. Trigonometric leveling relies on trigonometric calculation to determine height differences. This method is particularly useful for measuring heights in areas where challenging terrains are there, or when the distance between 2 points is too great for direct measurements. The vertical angles are measured by means of theodolite. The horizontal distance are measured by either using tape or chain, or it may be computed. The relative heights are calculated by using trigonometric formulas. So we can say that trigonometric leveling is the process of determining the different elevations of stations from observed vertical angles and known distance. Comparing the two methods, that is differential leveling and trigonometric leveling, both methods have their own merits and disadvantages. The choice of method depends on the specific project requirement, because trigonometric leveling is not limited to a horizontal line of sight. It is more flexible and provides faster elevation data calculation and collection as compared to differential leveling. Differential leveling offers high accuracy for short distance but requires a proper line of sight. Trigonometric leveling, on the other hand, can cover greater distance and is suitable for challenging terrains, but it may be slightly low accurate due to over-reliance on calculation and accuracy of the instrument that is used. Depending upon the horizontal distance between the stations, the trigonometric leveling may be classified into two categories: observation of height and distance as plane survey and observation of height and distance as geodetic survey. As we know, the shape of Earth is irregular and the approximate shape is ellipsoid. When we consider the spherical shape of the Earth at the time of doing surveying, it is known as geodetic surveying, and when the small distance is to be measured, we ignore this spherical shape of Earth. Such work is classified as plane surveying. If the distance between the instrument station and object is small, correction of Earth curvature and reflection is not required. And if the distance between the instrument station and the object is large, the combined correction, that is 0.0673 d square for Earth's curvature and reflection, is taken, where d is distance substituted in kilometers. If the vertical angle is positive, the correction is taken as positive, and if the vertical angle is negative, the correction is taken as negative. Let us see the various methods of determining the elevations of a point by using transit theodolite. There are mainly three cases to determine the RL of any point. The case 1 would be level ground and the base is accessible. Case 2 would be base of the object is inaccessible, but base of object is inaccessible, but the instrumentation station is in the same vertical plane as the elevated object. That means two stations are used and both stations are having the same height of instrument. Case 3, base of the object is inaccessible, instrument stations are in same vertical elevation, same vertical plane as the elevated object. To begin with, case 1, the base of object is accessible. Look at the given figure carefully. Locate point A, which is the instrument station, and suppose B is the point at some elevation, say h, to be observed. So h is the elevation of point B from the instrument axis, and d is the horizontal distance between point A and the base of the object. Let h1 is the height of the instrument and bs is the staff reading taken at benchmark, and alpha is the angle BA-C from the figure. So the height of instrument, as we know, is equal to RL of the benchmark plus the backside reading of staff at the benchmark. So RL of the point B will be height of instrument plus h. So if we look at the figure, it is absolutely clear that tan of alpha, that is equal to perpendicular by base, is equal to tan alpha is equal to h by d. We will cross multiply it. We get small h is equal to d tan alpha. So d is the horizontal distance, alpha is the vertical angle. So from this we can calculate RL of B is equal to RL of benchmark plus backside plus d tan alpha. If the horizontal distance between 2 points, that is point A and the object, is very large, then the curvature of the earth is also considered, and we will incorporate the combined correction. That is, we will either add 0.0673 d square or we will subtract 0.0673 d square. We have already discussed about the sign convention about the correction to be done. Now, coming to the last case, that is base of an inclined object that is accessible. So we have a special case here. The object is inclined and the base of the object is accessible. And in this case, we have to make certain assumptions. The horizontal distance between the foot of the object and the instrument station can be measured. The foot of the object and the instrument stations are in one line. So these are the two assumptions, and let AB be an inclined tower and x is the distance between the foot of the tower and the projected point B dash of its top B on the ground surface. So B dash is the projected point and B is the top point. So B dash will be on the ground surface. And C and E are the instrument stations such that C, A and E are in straight line. Considering the figure, D1 and D2 are the horizontal distances of the foot of the tower from the stations C and E respectively. Let S1 and S2 be the staff readings of the staff readings held at the same benchmark from two instrument stations. So from first setup we are getting the backside reading as S1, and from second setup we are getting the backside reading as S2. We also measure vertical angles from the stations C and E. Alpha 1 and alpha 2 are the angles of elevations from station C and E respectively. So consider the left side of the figure setup, that is the instrument is at station C. So the RL of benchmark plus the RL of benchmark will be height of instrument plus S1, that is the staff reading held at benchmark, and RL of point B would be height of instrument plus D1 minus X tan alpha 1. And considering the right side, when the instrument is at station D, RL of point B would be H1 or the height of instrument plus D1 plus X into tan alpha 2. So height of the instrument, as we know, RL of benchmark plus S2. Since we are considering our instrument to be at station D, for height of instrument we will consider the staff intercept taken from station D on the benchmark. So we have two equations, we will equate them. So we get S1 plus D1 minus X tan alpha 1, equate this to S2 plus D2 plus X tan of alpha 2. Or we can bring both the staff intercept on one side and tan values on the other side. So we get X is equal to S1 minus S2 plus D1 tan alpha 1 minus D2 tan alpha 2 divided by tan of alpha 1 plus tan of alpha 2. Quantities on the right side of the equation is known. So the value of X can be calculated, and once the value of X is calculated, we can easily calculate the RL of point B, that is equal to RL of benchmark plus staff reading S1 plus D1 minus X tan alpha 1, or we can write RL of B is equal to RL of benchmark plus S2 plus D1 plus X tan alpha 2. So from either side we can calculate the RL of point B. Let us take a question from our textbook Agor. An instrument was set up at A and the angle of elevation of the top of an electric pole, say BC, was 24 degree 36 minutes. The horizontal distance between A and B, the foot of the pole, was 600 meters. Determine the RL of the top of the pole if the staff reading held at benchmark was 2.532 meters. Assume that RL of benchmark is 100 with the telescope in the horizontal plane. It is always suggested to draw a sketch of the given situation, and we can see from the figure that the angle 24 degree 36 minutes is measured above the line of sight. So to get the RL of point C, the first thing we have to do is to find the height of instrument, to find the level of the line of sight, and to that we will add the H1, that is the value above the line of sight. So the height of instrument is equal to RL of the line of sight is equal to RL of the benchmark plus staff reading at that point. So it is already given as 2.532 and RL of benchmark is 100. So we need to calculate H1. So from the figure triangle A'(B')C, we get H1 is equal to A'(B' tan alpha or tan of 24 degree 34 minutes. We'll cross multiply it and we'll try to solve it. We get H1 is equal to 274.702 meters. So RL of point C, that is top of the pole, is equal to height of instrument, that is RL of benchmark 100 plus backside reading 2.532 plus the value of H1 that we calculated using trigonometry is 274.702. So it works out to be 377.234 meters. Now we will take up case 2, that is the base of object is inaccessible. Instrument station in the vertical plane as the elevated object, means there will be two instrument station and the object, all the three are in the same vertical plane as the elevated object, but the base of the object is inaccessible. When it is not possible to measure the horizontal distance between the instrument station and the base of the object. So again here there could be two cases. The instrument axis, that means two instruments that we are using, two setups we are using, both the instrument axis are at same level, and in the second case instrument axis will be at different level. So we are going to use instrument twice, and in case 1 the instrument axis are at same level, and in case 2 it will be at different level. And we can very well understand that the case 1 where the instrument axis are set at same level, which is very hard to achieve in reality. So case 2 seems to be more useful from practical point of view. But we will start with case 1, that is the instrument axis are at the same level. So look at the figure and if possible try to draw it. So the situation is, we can measure small b, that is the distance between two instrument stations, which is the horizontal distance between the two instrument station. Angle alpha 1 and angle alpha 2 would be measured from the two setup or two instrument station, and we can find the value of b. And what is the objective? Our objective is to find the value of small h, which is the elevation of the top of the object from the instrument axis. So A and B are the instrument points. Small h is the elevation of the top of the object from the instrument axis. B is the horizontal distance between A and B. Alpha 1 is the angle of elevation that is measured from A, that is first station, to point B, and alpha 2 is the angle of elevation that is measured from second setup instrument station B to the value object at P. So from triangle PA dash P dash, we find that tan of alpha 1 is equal to H by D, and we can cross multiply, we get H is equal to D tan alpha 1. Similarly, now we will consider the other triangle, that is P B dash P dash. Here we will see that tan of angle alpha 2 will be perpendicular by base. Perpendicular is small h, whereas the base is small b plus d. So again cross multiply it, we get H is equal to B plus D tan alpha 2. Now we have two equations, equation 1 and 2, we will equate both of them. So we get D tan alpha 1 is equal to B plus D tan alpha 2. So we will rewrite it, and eventually we solve and get D as B tan alpha 2 divided by tan alpha 1 minus tan alpha 2. So we will put this value, the value that we obtained for capital D, in the above equation, that is H is equal to D tan alpha 1. So we can write small h is equal to B tan alpha 1 into tan alpha 2 divided by tan of alpha 1 minus alpha 2. So RL of point P will be RL of benchmark plus backside reading plus H. From the figure you can see that alpha 1 will be always greater than alpha 2. Now the second case when the instrument axes are at different level. In the field, it is difficult to keep the height of instrument at same level. The instrument is set at different stations, and the height of instrument in both cases are recorded by taking backside on the benchmark. Point to note here is that the instrument setup 1, 2 and the object in this case are in the same line, or to be more precise, they are in the same vertical plane. So again there can be two cases. The height of the instrument axis of the instrument which is nearer to the object is lower. That is, the object and the instrument setup which is nearer to the object is lower. And in the second case, height of the instrument axis of the instrument which is nearer to the object is higher. So these two cases we will consider. Height of the instrument axis of the instrument nearer to the object is lower than the instrument that is farther from point A, in our case, is lower than point B. So from the figure P A dash P dash, we find that tan alpha 1 is equal to H1 by D. So we'll rearrange it, we get H1 is equal to D tan of alpha 1. Similarly, from the other triangle, that is P B dash P dash, tan of alpha 2 is equal to H2 divided by B plus D. So we get the value of H1 and H2. H2 is equal to B plus D tan alpha 2. Now HD is equal to, from the figure you find HD, that is equal to H1 minus H2. So we'll substitute the values of H1 and H2, we get D tan alpha 1 minus B plus D tan alpha 2. We take out D common and rearrange the equation, we get the value D is equal to HD plus B tan alpha divided by tan alpha 1 minus tan alpha 2. Now substituting this value of D in our original equation, we get H, that is D tan alpha 1. So we get value as HD plus B tan alpha into tan alpha 1 divided by tan alpha 1 minus tan alpha 2. Height of the instrument axis of the instrument nearer to the object is higher than the instrument set farther from the point A, in our case, which is higher than point B. So if we consider the triangle P A dash P dash, we get tan alpha 1 is equal to H1 by D, and we get H1 is equal to D tan alpha 1. So this is our equation 1. From the other triangle, that is P B dash P dash, we get tan of alpha 2 is equal to H2 divided by B plus D. So we will solve it. We get H2 is equal to B plus D tan alpha 2. Now we know that HD is equal to H2 minus H1. We have the two values H2 and H1. We will substitute in this equation, rearrange it, take D common and divide the values. We get D is equal to HD minus B tan alpha 2 divided by tan of alpha 2 minus tan of alpha 1. Now like in previous case, we will substitute the value of D in H1 is equal to D tan alpha 1. We get the value of H1 as HD minus B tan alpha 2 in bracket multiplied by tan alpha 1 divided by tan alpha 2 minus tan alpha 1. Coming to case 3, when the base of object is inaccessible, instrument station are not in the same vertical plane as the elevated object. So it is a complicated situation. Base of the object is inaccessible, so you can't measure the horizontal distance, and the instrument are also not in same vertical plane. So let us consider our case. A and B be the two instrument station not in the same vertical plane as that of object P. So the logic will be same. We'll form some right angle triangle, we'll measure some angle, and distance can be measured by using trigonometric equations. So select two stations A and B on a level ground and measure B, horizontal distance between station A and B. Set the instrument at A, level it, set the vertical vernier to 0 degree, 0 minutes, 0 seconds, bring the altitude bubble at the center and take the backside as HS on the staff held at benchmark. We get the value which we will mark as height of instrument is equal to RL of benchmark plus backside. Measure the angle of elevation alpha 1 from point A towards object P. This angle will call BA dash as alpha 1. Now shift the instrument to point B and measure the angle of elevation alpha 2 at B. Also measure the horizontal angle. From a station, we are not just measuring vertical angle alpha 1 and alpha 2, we are also measuring horizontal angle theta and alpha between horizontal angle between angle ABC and BAC. So we get from the triangle ACB is equal to 180 minus theta plus alpha. So all the values are known to us now. We'll apply trigonometric relations in triangle ABC, angle BAC is equal to theta and the value AB is equal to B, applying sine law that when we know three angles and one side, we can easily use sine law. By using this, we get BC is equal to B sine theta divided by sine of 180 degree minus of theta plus alpha. Similarly, AC will be B sine alpha divided by sine of 180 minus theta plus alpha. So we have found the values of BC and AC from the triangle. Similarly, when AC and BC is known, we can find the value of H1 and H2. We also know the value of angle of elevation alpha 1 and alpha 2. So H1 will be AC tan alpha 1 and H2 would be BC tan alpha 2. So values of AC and BC are obtained from the above equations. So the RL of point P will be height of instrument at station A plus H1, or we can say that RL of point P will be equal to height of instrument at station B plus H2. We can use the set of values from either station A or station B. So height of instrument at station A is RL of benchmark plus backside reading recorded at benchmark, and the height of instrument at station B will be RL of benchmark plus backside reading held at benchmark.